Hi everyone, in this video we'll be looking into mass spectrometers, which is a key part of the IB chemistry syllabus. But before we start off with anything, what is a mass spectrometer and what exactly does it do? Well, the functions of a mass spectrometer kind of divide into a number of things, but we can essentially say that it does a couple of things. Firstly, it measures the relative atomic mass of isotopes. Not only does it do that, but it actually finds the relative abundances of isotopes that are inside a sample of an element. And by doing that, we can kind of find out what that element is really made out of. Not only this, but it also identifies what is the finer structure and relative masses of molecules depending on how they break in the process, and ultimately the broken patterns show up as fragmentations that are detected on the detector, which is the final stage of the mass spectrometer. Now, knowing this, there are a couple of steps in the mass spectrometry process that we need to know. Firstly, we have the step vaporization, and then we move on to this step called ionization, and then we have acceleration, denoted by the number 3, and then we have deflection, number 4, and finally we have the stage of detection. We'll be going through all of these stages one by one, starting off with vaporization. Now, in some of our previous videos where we've looked into IB chemistry, we've kind of defined vaporization as the sort of umbrella term wherein any of the substances, regardless of which phase they are in, end up becoming gas. We've kind of specifically defined evaporation and boiling as processes wherein we have substances transition specifically from the liquid phase in a gas phase. However, vaporization is an umbrella term, so therefore, regardless of which phase they start in, regardless of whether it's solid, becoming gas, sublimation, we call all of those processes vaporization as long as the end product is gas. So we will be having vaporization as the first stage, and what happens here is the sample will end up in a gaseous form. And in order to get the sample in the gaseous form, we will be using a heater in order to vaporize. And so it would kind of look like us creating gaseous atoms from whatever state the substance was in. So it would pretty much look like this. And because we're breaking the covalent bonds in the molecules to produce gaseous atoms, we're going to require amounts of heat, relatively greater amounts of heat than anything. So we will call this process fragmentation as well, because we're breaking the covalent bonds. And so, for instance, if we are talking about chlorine molecules, we will be having chlorine molecules to start off with, breaking the covalent bonds in the chlorine molecules in order to form chlorine atoms. And these chlorine atoms can be Cl35, Cl37, depending on which isotope of chlorine they are. But essentially, we will be breaking the covalent bonds in order to create gaseous individual atoms. Of course, not all molecules may break in this process, but still, we will try to break at least a lot of them in order to create as much gaseous atoms as possible. And the reason why we do vaporization and try to get these elements in their individual single atom state is because we want to detect each of these relative atomic masses of each of these isotopes. Because we try to detect relative atomic masses, we need individual gas particles, not them kind of collected in single solid states or kind of merged together in liquid phase. Secondly, we're going to have the process of ionization. And you can kind of really just understand this process as kidnapping an electron. And what happens is we will essentially be having a sample that's bombarded with a stream of high energy, really fast moving electrons from what is an electron gun, and this is going to knock off the electron from the atom in order to produce a positive ion. So the sort of equation for this process would look like us having the substance in its gaseous atom form, creating a positive ion, a single gaseous ion, and then also getting rid of one electron in this process from the single atom to create this positive ion. Of course, we may produce ions with not only a single positive charge, but with perhaps 2+ ions, 3+ ions, etc. But mainly we aim and strive for this state. Thirdly, we have the process of acceleration. And in this process, we will be using an electric field. We'll be using an electric field to accelerate the positive ion towards the magnetic field. And then after the process, these essentially accelerated ions will be passing through a little slit. and this is going to create what is a very narrow beam of ions directed towards this magnetic field, directed towards this magnet, wherein we enter the fourth stage of the process, which is deflection. Now, deflection is basically these accelerated ions being deflected into the magnetic field. And the amount of deflection really depends on a couple of things. But essentially, the amount of deflection is going to depend on the mass of the positive ion and the charge, as well as the velocity, and also the strength of the magnetic field. We will essentially have deflection when the mass of the positive ion is lesser and the charge of the positive ion is greater. And we kind of define these two variables in the single sort of term called mass to charge ratio. And if we have lower values of mass to charge ratio, i.e. we have lower values of mass, higher values of charge, that will result in the greatest amount of deflection. Lastly, we have the stage detection. Now, all of these ions are going to be deflected in the magnetic field and then kind of be detected by the detector. And these ions are going to be read by the ion current detector.